preliminary example that we took up at the end of the previous class, in which we made certain ad hoc assumptions knowingly, as I said, just for pedagogic purposes. And the main thing there was that we ignored W2 and W3, which are the warping in the plane of the cross section. The other thing that we did also was to assume that W1 has a form such that it's a function of x1 multiplied by a function of x2 and x3, the cross-sectional coordinates. Okay, so those were the ad hoc assumptions. We also derived the position vector for the undeformed configuration along with the corresponding covariant and contravariant base vectors. Now we will take up the same thing as far as the deformed beam geometry is concerned. So we are done with this undeformed state. Now we are focusing on this deformed state. Basically, the first thing that we look at is the rigid body like translation. So there's a displacement vector that you see over here, u, which takes this r from the undeformed reference curve to the deformed reference curve, big R. And so that's basically the difference between this position vector big R and the position vector small r, which we call as u. And that because it's a function of points on the reference curve for which the coordinate is x1, that vector u is a function only of x1, which means that both its magnitude and its directions are basically functions only of x1. So ui and pi are functions of x1. So the position vector to points on R, obviously R basically the position vector to the corresponding point on the reference line in the undeformed reference line, and then adding to that the displacement vector that we just introduced. And in whatever we have towards this particular example, as well as the next example, general example that we will take without the ad hoc assumptions, I'll try to use some color coding. I might have missed at certain places, but as far as I remember, I have included it everywhere. I'll use this light green shade to refer to configuration of the undeformed state, the dark red basically to refer to the deformed state, and anything which happens in between them, taking from the undeformed to the deformed, I will use a yellow. So going from the green to the red using an yellow, using the traffic signal as basically the yellow being intermediate between the green and the red, so that things become a little more clearer. But most of these variables have already been introduced to you, so I hope things are clearer. As usual, you are welcome to stop me in between to get some clarifications. So for this simple example with the ad hoc assumptions, as we introduced, one of the ad hoc assumptions was the St. Venant warping function, which was for the local cross section. So at any given cross section which is identified by x1, you have lambda as a function of x2 and x3 is the St. Venant warping function. This typically will be determined in simpler beam theories by just the shape of the cross section. For example, in a rectangular cross section, it would be just x2 times x3 with an appropriate sign. So that is basically how the St. Venant warping function is typically introduced, and there are ways of determining it for certain regular shaped cross sections, some of which you would have been introduced to in the flight vehicle structures, I hope. So the other aspect is, of course, to determine the out-of-plane warping is its amplitude, which is a function purely of x1. So xi is a function of x1, and as we have already mentioned, we are restricting here to the out-of-plane warping, that is basically W1. So W1 is given by xi times lambda. So now the position vectors to any point in the deformed beam can be obtained, because we know W2 is 0, W3 is 0, W1 is given by lambda times xi. We also know what has happened to the reference curve itself, and in addition, of course, there has been a rotation. So the position vectors to the points in the deformed beam can be found this way. Of course, this is for an arbitrary material point. It is given by first identifying the location of that point in the deformed reference curve, which is given by this uppercase R, and then you have, just forget this for a moment, you have basically x2 and x3 along your small b2 and b3, and your wi's, which is w1, w2, w3 along b1, b2 and b3. of which of course we are going to drop out W2 and W3, but in the general case it basically is X alpha B alpha plus Wi Bi, and the reason why we are doing it this way is because we introduce the right stretch tensor, which means that the stretching happens before the rotation happens. So basically this is what happens. There is a stretching because of the warping which is happening within the cross section, and then that is rotated from the small b system to the big B system. So that's basically what happens. Then you get the position vector to any arbitrary material point, which is this r hat on the deformed cross section, which is basically the surface, the shell-like surface with the blue tinge. So now we know that this is a scalar number that can come out. So CVB times B alpha is by definition of the deformation gradient tensor here, nothing but the big B alpha. Similarly, this Bi also becomes the big Bi. So this is quite straightforward to see. So though in most of the rest of the classes you will basically see, you will not revisit this, how this came. We will directly take this. So some people get confused that the Wi's are along big Bi. So that's a mistake you should avoid. Remember that Wi is actually along the small Bi's because the vector, it doesn't matter. But once you have put it in the form of scalar measure numbers, you should be aware which basis it has been expanded in. It has been expanded in the small Bi, but because of the fact that we are bringing it back to this big B systems, that's why you have this operation with the finite rotation from the small b to the big B, and therefore it appears as if your X alpha is along B alpha and Wi along Bi, which is again a different way of interpreting it, which is also possible. But the way Wi is defined is, for example, the vector W, the warping vector, dotted with the small Bi. So that's how the small Wi's are defined. So that's important to remember. So then in this particular example, since we drop out W2 and W3 and take W1 as lambda times xi, introducing the St. Bernard warping function lambda, so this is what it becomes. Now we also, for compactness of notation, we define the partial derivatives of lambda. Remember, lambda is a function of both x2 and x3, the cross-sectional coordinates. So the partial derivative with respect to x alpha will be denoted hereafter as just lambda subscript alpha. Now you might recollect in the undeformed configuration, what we did in the class is to introduce the concept of the initial curvature in the same way as the angular velocity, and we said that Bi prime is given by small k cross Bi, where small k involves is the vector which basically involves the initial twist and the curvatures, and the initial twist in general can also involve the torsion of the reference curve in case the curve is not planar. So that's basically what it was, and we took advantage of another fact that r prime is nothing but V1 because that's the unit tangent vector. Now we have a similar kind of a situation in the deformed state. So what is that? So that basically involves once again an r prime and a big Bi prime. The big Bi prime is much easier to see. So big Bi prime is given by the big K cross big Bi. So this big K plays a similar role what the small k plays, and this is again a vector equation. Doesn't matter in which expansion you have the small k or the big K, doesn't matter. These are basically used as vectors over here. That's why you have the cross product. So basically, you when you are going to get the deformation gradient tensor, you need the covariant basis vectors for the deformed configuration, for which we'll actually have to take the derivative of r hat with respect to each of the cross-sectional coordinates x1, x2, x3, and we take with respect to x1, we basically get the prime. So we would need b alpha prime and b1 prime, etc. So when we do have those things, at that time we can substitute in terms of the k and basically bring in the so-called one-dimensional deformation generalized strain measures into picture, because this big K contains the initial twist and curvature as well as the additional curvatures which have ensued because of the load, which is basically the twisting due to the torque and the bending curvatures due to the bending moment. So that's all included in that. Of course, in a composite there will be further complications, one coming because of the other, etc. then we would also need here R prime. For example, when we are determining big G subscript 1, you would need the partial derivative of R hat with respect to x1, then you would need R prime. So that's why we bring in this particular formula whereby we introduce the concept of the axial strain and the transverse shear strains of the reference line. So that's basically what it is. So let's take a simple example where there is no transverse shear deformation, in which case the gamma 1 alpha will be 0. So you basically forget this term, and you basically see that your R prime is then, if there were no transverse shear deformation, your B1 would be tangential to R, because it's a transverse shearing deformation which makes the cross section to rotate further, and so that the normal to the cross section no longer remains normal. The additional rotation that you get is what is gamma 1 alpha about the appropriate directions x2 and x3. So if you leave that aside, it obviously R prime should be parallel to B1, but it no longer be a unit vector because of the fact that in general this reference curve would have gone through a stretching as well, and that stretching is the reason why you now have a different arc length coordinate. Instead of x1 along the undeformed configuration, you have S along the deformed reference curve. So that is basically has to be taken care of, and that is why we introduce this extensional strain of the reference curve. And this quantity is a function only of x1, because remember, it's something which is happening to the reference curve, not to the beam as a whole or to any arbitrary material point within the beam. So that's basically what it is. Now the fact that there is an additional rotation basically means that your R prime is no longer going to be tangential. So rather B1 is no longer going to be B1 is tangential, but B1 is not tangential, but your R prime will now have a B2 and B3 B2 and B3 components, and those components will be dictated by your transverse shearing strain, which is basically gamma 1 alpha refers to the tensorial shear strains of the reference curve, or rather the reference cross section, because it's something which is associated with the cross section, how much it rotates away from the tangential point. So that's basically accounted for this gamma 1 alpha, and therefore it has two components. Once again, it's an implied summation over alpha equal to 2 and 3. So now we introduce the concept of the 1D generalized strains. Already we have talked about it. There is gamma 1 1, 2 gamma 1 2, and 2 gamma 1 3. And in a lot of this variation asymptotic method related literature, it is typically called as the force strain. The reason is that it is conjugate to the generalized the forces actually associated with the section, that is basically the axial force and the two transverse shear forces, and that's why they're called in this way. And this is somewhat similar to the concept of the work rate conjugates that we introduced in terms of the stresses and strains at the 3D level. This is an equivalent thing at the 1D level. So in the previous slide we saw already that Bi prime is equal to K cross Bi, where K has components K1 B1, K2 B2, K3 B3, which means the measure numbers Ki are along big Bi. So these are again things that you ought to note down, because these are very critical. Which vectors are expanded about which unit vectors in order to get the corresponding measure number. So if you remember, W for example was expanded along the small b system, whereas the K is expanded along the big B system. All of these are not sacrosanct. It's just that you have, once you still have something, you follow it strictly. The fact that we are introducing these expansions over different sets of unit vectors, the reason is that the compactness of the final results. So if you choose the measure numbers to be along the big Bi basis, then in terms of those Ki, the equations turn out to be much simpler than if you were to introduce in terms of the small Bi. Similar is the case with the warping as well. It's better to introduce it along the small b system. And one of the reasons for that, of course, is the fact that we introduce the right stretch tensor instead of the left stretch tensor. So coming back to K, it's the curvature vector for the deformed beam reference line. So that is its formal name. and the measure numbers of k, which is basically these ki, should be noted, are basically are not Eulerian, but they are basically Lagrangian, because they are basically with respect to x1 rather than with respect to s. So this is again another difference you have to remember. One is the fact that the measure numbers are about the big B's, and the other is that unlike some of the literature that you might come across in the non-VAM related theories, where the Eulerian curvatures are typically used. In this case, the way we have introduced them, it is actually the Lagrangian curvatures. In other words, things are with respect to the undeformed configuration. So the curvatures and twist, for example, is per unit length of the undeformed beam rather than per unit length of the deformed beam. Next, of course, like we do with many of the measure numbers of vectorial quantities, we introduce the tilde matrix, the antisymmetric matrix containing the measure numbers of the total curvature. So this is the curvature which results in the end, so it includes the initial curvature in it as well. So this is basically again obtained in a similar way using the permutation tensor that we have discussed quite a few times earlier. Now coming to the relationship between k tilde and the direction cosine matrix is basically very similar to what we had for the angular velocity. For example, you remember that an omega tilde, for example, was given by a CBB dot with, multiplied by CBB. So it's a similar thing to that, just that now we have the initial twist and curvature as well. So that basically is this. And because k is expanded in the big B basis, we want to convert this also to the big B basis. And the way it is represented as a matrix is basically an expansion of a tensorial quantity, a dyadic, and therefore you need two expansions. So basically you're converting from the small b to the big B. Remember that the k is in the small b system, so you're converting from small b to big B and small b to big B on both the sides. So basically you're getting something in the entirely in the big B system. So if there were no initial twist and curvature, it's very easy to see the analogy that you basically have. But even when in the situation where you have initial curvature and twist, you can think of something like the initial, or rather an angular velocity associated with the original frame itself. So in the case of a helicopter, for example, apart from the rotation of the cross section, which can be time varying, there is the rotation of the blade itself which has to be taken into account, which is what would come in a similar kind of a relationship. Next, the 1D generalized strains, which are the force strains. So gamma 1I, basically I ranging from 1 to 3, so there are 3 of those quantities. These are called the 1D generalized strains or force strains, explicitly found from the equation that we had in the previous slide already. So that's how we introduced the concept of gamma 11 gamma alpha. But there are many other equivalent ways of introducing the same. We will see one of the vector dyadic relationships soon. So if you expand that out, and we can in your book you can see that there are many equivalent relationships, and you can also see by simple algebraic manipulations or matrix manipulations you can go from one to the other. Now this is for example how gamma 11 is related to the UIs. So which is basically the remember the displacements of the reference line. So that is u1, u2 and u3, which are functions of x1. Now suppose you didn't have, let us say, initial curvature and you didn't have any rotations. In such a situation you would have the direction cosine matrix as an identity matrix. So in other words, your C11 would be 1, and therefore this 1 would cancel with that. And in this, C12 and C13 would be zeros, so only C11 would be left, and that would multiply just a U1 prime. So C11 would be 1, and that's multiplying a U1 prime, so you would see that gamma 11 is equal to U1 prime, which is something you are very familiar with because prime is a derivative with respect to the x1 direction. So it's quite obvious that your gamma 11 is equal to u1 prime. So that's a case where you don't have any rotations. But once rotation comes into place, the equation becomes nonlinear, and the rotation would in turn affect what is the value of your gamma 11. So there would be nonlinear terms adding up to that leading term u1 prime, and that's basically what this particular equation is. So as far as this equation is concerned, or for that matter, this equation or the vector dyadic equation that we would have for the vector gamma, of which these are the measure numbers. In all such situations, you would see that these are all exact relationships for a curve undergoing any kind of deformation. So in other words, these are so-called geometrically exact relationships for the strain displacement. Again, if you recollect the 4 classifications that we had in terms of the load, stress, strain and displacement, this is nothing but the strain displacement relationship, because you have the 1D generalized strain here related to the displacement, and there is also a rotation which is contained in this. That's why you see all of these are in yellow color basically. These are all associated with displacements and rotations, how they are related to the 1D strain, and all of these quantities are 1D. Whether you talk about the U's or C's or gamma 11, all of these are one-dimensional quantities. So in other words, it is a one-dimensional strain displacement relationship. Similarly, you should have relationships for the gamma 1 alpha and the kappas as well. So this is the relationship for the transverse shear strain of a reference cross section. This is the additional rotation which it undergoes, which is a very small rotation when compared to the overall rigid body-like motions that the cross section undergoes. And I've been also telling that there are 2 ways of taking care of these transverse shear deformation. Either you can treat it along with the other 1D strains, namely gamma 11 and kappa 1, kappa 2, kappa 3, or you can treat it as part of the warping. So in fact, in the 2 examples that we are taking up, one is this preliminary example where we are making ad hoc assumptions, and in the general example we will do 2 alternate ways so that you are exposed to both of these methodologies. So coming back here, now in this case we are treating the transverse shear strains as separate 1D strains. In other words, it is associated with rigid body-like motions rather than with the warping. So here you have gamma 1 alpha related once again to the direction cosine matrix and the U's, and when initial curvature or twist is present, the equations get a little more complicated as well. So you can see a clear analogy between these 2 equations, except for the fact that there is no removal of -1, which basically, because in the case where there is no rotations and identities, whereas these are off-diagonal terms, and so that is not there. But otherwise you see a one-to-one correspondence between these 2 ways. And again, this will be also in synchrony with the vector dyadic definition, which will be much more compact for the 1D strain. We'll introduce that shortly as well. But before that, let's go ahead and do a similar thing that we did for the undeformed configuration, where we found the covariant and contravariant basis vectors. In this case, the contravariant basis vectors are not necessary. You only need the simpler covariant basis vectors, and that's what we'll determine over here.
So by rotation, as you said, that is it referring to that rigid body like rotation? The first term, contribution of that first term in the previous slide, and these expressions, gamma 1, 1 and...
You're talking about this gamma 1 alphas?
Yeah, the first, after that, like first term which...
Yeah.
So is that the contribution?
Yes, that's correct. So here, in this way of tackling the problem, we are not allowing this to be a part of the warping, we are allowing it to be a part of the rigid body-like rotations. So it is an additional rigid body-like rotation which is basically contributed over here. So as you know, see small b to big B is nothing but an entirely a rigid body-like rotation. So that basically takes care of that part of it. But the fact that there is this U also which is contributing to that is basically that this is nothing but a difference between the rotations of the cross section and the rotation of the reference curve. So that's why you see the effect of U coming in as well.
But sir, intuitively speaking, like when you compute this potential energy like term, so that actually will not get affected by some rigid body like rotation or rigid body like motions.
Yeah, it will not, right?
So, but in this case, like if we have some non-zero term over there, so that finally will affect expression.
No. See, once again, let me stress that these are not rigid body rotation, but rigid body like, because of the fact that 2 cross sections are rotating in general different from each other, because they are functions of x1. All of these quantities are functions of x1. Okay. So it's because we are only focusing on a particular cross section now, it appears as if it is a rigid body motion, but it's not in reality a rigid body motion, and therefore it should contribute to the strain energy. This would be different from, let's say, the helicopter itself having a rigid body like motion. That should obviously not contribute to the strain energies. Or if the, let's say, the helicopter rotor blade was fully articulated like the older helicopters, then the blade could have some kind of a flapping or lead lag or a torsion about the bearing. So all of these would then be rigid body like motions of the cross section, should not contribute to the strain energy of the
kinetic energy.
Exactly, right. So let's go and determine the covariant basis vectors of the deformed configuration. Once again, the definition is very similar. You have to take the partial derivative of the position vector of any arbitrary material point at x1, x2, x3 with respect to each of the cross-sectional each of the coordinates x1, x2 and x3, and all of these derivatives, because it's a derivative of vector, it has to be specified, and this happens to be in the frame A. Okay, whose motion itself we know, it could be the aircraft fixed frame in our case. So this is basically big G subscript I, big G referring to the fact that it's a deformed configuration. And we have to, in order to determine that, of course, we have to carry out the differentiation, for which we take the expression for r hat that we formulated in one of the previous slides. So that's basically r plus ui bi, which basically identifies the point on the reference curve and the reference cross section at in the deformed configuration. So that is your big R. So we are breaking that up into two parts, R plus U. And then, of course, because of the multiplication by CBB, this x alpha, which was along small b alpha, and lambda xi, which was along small b1, became along the bigger b alpha and big b1. So that's basically what we have. And so this is your R hat, whose differentiation we will now carry out with respect to each of the x's. So first, with respect to x1, so there we have to utilize the fact that r prime is equal to small b1, for example, and the definitions for the 1D strains that we introduced, and a little bit of manipulation, and then you will see that you can convert this entire thing instead of the small b system in everything into the big B system. The reason is when we go to the deformation gradient tensor, remember that we are going to expand it to get its measure numbers in a mixed basis, where we are going to expand this part, that is the deformed configurations covariant basis vector, along the big B system. So we need to get its measure numbers along big B1, big B2 and big B3. So basically we can take the differentiation with respect to x1 in the frame A and convert everything to the big B system. When we do that, basically the B1 component consists of the of course the identity, because in a case where there is no deformation, basically it should agree with what it was in the undeformed configuration, and that's why you have that unity there. You will have that in the corresponding term of B2, for example, of G2, etc. So now coming back, there is the contribution of the extensional strain of the reference line, and through K2 and K3, which are the final curvatures, there is the contribution of kappa 2 and kappa 3, which is basically the additional bending curvatures which have come in addition to the initial curvatures of small K2 and K3 that were already there. And then, of course, the contribution from warping, which will be indeed very, very small, because of the, first of all, the warping itself is a small variable compared to, for example, the U's which contribute to gamma. In addition, there is a derivative with respect to x1, which is having an order of magnitude of L, which is the length of the beam, and therefore the contribution from that will be very small. This is all exact, so we are basically writing out everything that appears in the entire thing. Of course, there is an approximation, because we have converted the W1 into a lambda times xi, where basically xi depends only on x1 and lambda depends on x2 and x3, and we have left out W2 and W3. Otherwise, there would have been contributions from those as well. Similarly, you have a B2 contribution, where primarily both in the B2 and B3 contribution, you can basically see that there is a contribution from the twist, which is not over here. Here you have basically the bending contributions contained within K2 and K3. Here you have contained within K1 basically the contribution from the twist per unit length because of the torque that is applied, for example. Okay, so then in addition you also have the contributions from the transverse shear strain of the reference cross section. So that's your gamma 1, 2 and gamma 1, 3. And once again the warping, just as it contributes to the V1 component, contributes to the V2 and V3, but this time without a derivative. So it sometimes could be possible that this can make a difference to the whole thing. We will see some specific examples of that when we go to let's say a T class or S class beam. Next, the other things are much simpler because the only way through which x2 or x3 enters, because we have to take, already we have taken a derivative with respect to x1, the next is with respect to x2. The only place where x2 enters is through this and through lambda, because lambda is the same finite warping function of both the cross-sectional coordinates x2 and x3. So it is only through x alpha here, or rather x2 here and lambda here, that it basically has these two contributions. So similar thing with respect to x3 and therefore the big G subscript 3 as well. Next, the 1D generalized strains, gamma 1 and 2 gamma 1 alpha, which we introduced earlier as a derivative of this, basically this big R prime in terms of its components along V1, V2, V3. We basically said the V1 component is dictated by your gamma 1 and the other two by the transverse shear strain measures gamma 1 alpha. Now there is an equivalent, more compact way of introducing it by means of a vector dyadic notation, which is what we will do here. So we'll first mention what is the physical meaning of this. So the 1D generalized strains gamma 1 and 2 gamma 1 alpha can be interpreted as the measure numbers along the small b system, that is along the undeformed configuration of a particular vector. What is that vector? That vector is the difference of two vectors, and the first vector there is associated with the deformed configuration, the second vector is associated with the undeformed configuration, and the second vector which is associated with the undeformed configuration is nothing but r prime, that is basically the tangential vector to the undeformed reference curve. Similarly, you have the tangential vector associated with the deformed configuration, which has to be nothing but the derivative of r with respect to s, okay, because s is the new arc length, but instead you have pulling back r prime, that is the derivative of r with respect to x1, because you want to know what change has occurred. So that has to be brought about. So you are taking r derivative not with respect to s, which would have given the tangent vector anyway with respect to that. Instead you are basically taking an r prime and then you are pulling it back to the small b system. Remember that r prime is associated with the deformed configuration. It is in the big B. So you are pulling it back to the small b so that you can subtract this, which is already in the small b. Only then you can enforce this particular thing. Once you do that, you get a new vector, and that vector, when you expand in the small b basis, what you get are nothing but these components, that is gamma 1, 2 gamma 1, 2 and 2 gamma 1, 3 along small b1, small b2 and small b3 respectively. Or in other words, in a vector dyadic form, the relationship between the 1D strain measures, what we call as the force strain measures, that is basically gamma, which is written in a vector form. So when you write it, you will basically, this is in bold, so you will basically underline that. So that basically is given by the finite rotation tensor, which is basically going in a reverse. And this is the reason why we had that terminology of pull back for this, because in reality what is happening is we are going from the undeformed configuration to the deformed configuration, whereas here we are pulling it back from the big B system to the small b system, or in other words from the deformed configuration to the undeformed configuration. So it's a pullback. So we are performing a pullback on the r prime and removing the r prime which was already present in the undeformed configuration. So that will basically give you your gamma. So you can see a very simple example where there is no rotation. If there were no rotation between the small b and the big B system, it's one and the same, then it just becomes big R prime minus small r prime. That's quite intuitive. And just that because we have finite rotation, those rotations are not small, basically you have this term, the dot product here becomes very important. Next, we'll look at the deformation gradient tensors, measure numbers, and these are measure numbers, of course, in the mixed basis of the big B and small b system, because that's a second order dyadic. We need two bases. So that's what we refer to as chi subscript ij, where I and j vary from 1 to 3, and that is given because the deformation gradient tensor chi is given as gk, where k is a dummy index and there's an implied summation over that. And now we bring in the mixed basis. So here we have the small b system and here we have the big B system. So instead of calculating this as a juxtaposition, we are now able to calculate this as a scalar quantity, this as a scalar quantity, multiply those scalar quantities, and of course there is an implied summation over k, and then you get the ijth component of the deformation gradient matrix in a mixed basis. So let's recapitulate what we derived. So that's basically the earlier part of today's class. We got the big G1, big G2 and G3. We had written this as G alpha, we're just expanding it out as G2 and G3 over here. So these have only two components each along the big B vectors, and these have all three. And then in the previous class we had derived the contravariant basis vectors for the undeformed configuration, which are the small g's, but because they're contravariant, it's instead of a superscript, it's a instead of a subscript, it is a superscript. So G1, G2 and G3 over here expressed everything in terms of the small b basis. Now it's quite straightforward to take these dot products, because already the small g's are in the small b system, as you see here, and the big g's are in the big B system. So you have to just take this dot products and multiply each other. Okay, so first of all, chi 1 1, for example, you just take the one term over here and the one term over here, and then similarly for the second row and the third row, and you add all of them up, and basically you reshuffle them to put in a more compact form, and this is what you get as the first term of the deformation gradient matrix. So you have, once again, you see that this chi 1 1, which is what eventually you would primarily contribute to the 3D strain gamma 1 1, irrespective of whether it is a linear problem or a non-linear problem. This would be the leading contribution to your gamma 1 1, and so there you see that that is capital gamma 1 1, and there you see that one of the major contributions is a small gamma 1 1. So in other words, the extension of the reference curve is one of the major contributions to the extensional strain of the beam as a whole, okay, irrespective of whether the point is along the reference curve or any other point in the domain of the cross section. So that is one thing. And then there will be, for points which are away from this particular reference curve, that is for which x2 and x3 are non-zero, you would have contributions from bending, and bending also come into picture. Of course, here you have the initial curvature contained in this. When we go to the 1D strain, or rather the 3D strain capital gamma 1 1, you would see that that part is actually removed. So as of now, it is just a deformation gradient tensors measure numbers that we are looking at. So that's basically what you see there. And then of course the effect of warping, both its change with respect to the length and by itself because of the combination with the initial twists, that it has an additional contribution. The other terms are much simpler. Your gamma 2 1, for example, chi 2 1 along with chi 1 2 is what would contribute to the in-plane shear strain, that is gamma 1 2, and there that's why you basically see the contribution for the reference cross sections transverse shear strain as well. But in addition, you also know that the way a torque, for example, is resisted is by shear strain or shear stress in the cross-sectional plane, and because the cross-sectional plane is perpendicular to the one direction, that's why in the one direction, both in 2 and we will see that in 3 also, you have contributions from the twist. So your big K1 minus small K1 is nothing but your twist per unit length because of the loading, and that's basically going to contribute to your measure number over here. And once again, there is a contribution from the warping. Already this is small. Now that is getting further multiplied by K3, which in turn is small because it has kappa 3 and small K3, both of which are small quantities. So therefore, typically this will be a smaller contribution compared to this. In fact, even this in most problems would be a much smaller contribution compared to this. It's basically the twisting which contributes to the makes a large contribution to chi2 1 and therefore to capital gamma subscript 2 1. Next you have chi3 1, which is similarly formed from these sets of covariant and contravariant basis vectors after taking the dot products and adding them up. So basically you have a very similar situation to chi2 1, just that the 2 and 3 are basically interchanged with the appropriate signs. And then you get chi2 2 and chi3 3 equal to 1. This is a special case because we have left out the warpings associated with the cross-sectional directions. That is, we have said W2 and W3 are equal to 0. And because of that fact, we are getting the other two diagonal terms of the deformation gradient tensor expressed as a matrix in the mixed basis as equal to unity. In other words, nothing is happening in the 2 and 3 directions as far as this is concerned. If we had W2 and W3, these would have been different from 1, and there would be contributions directly from W2 and W3 into these. Now, similarly, chi2 3 once again is associated with warpings in the W2 and W3, but how they change with respect to the other. For example, this would involve W2 comma 3s and W3 comma 2s, and because W2 and W3 themselves are 0, their derivatives are 0 as well, and that's why you see that these terms are 0 as well. And finally, you have chi1 2 and chi1 3, which are basically off-diagonal terms but associated with the one direction. Because we have not taken W1 to be 0, we have taken it to be non-zero, and therefore you see the contributions of that coming in. And remember that lambda subscript 2 means that derivative of the center-nth warping function with respect to x2, and similarly derivative of center-nth warping function with respect to x3. So it's basically something like a W1 comma 2 which contributes to this, and a W1 comma 3 which is basically contributing to this. If you had no warping, you would see that, that is even the out of plane warping, you would see that these would have gone to 0 as well. So almost everything would basically be associated with chi I1. So the main strains that you're basically having, that is gamma 1 1, inside this kappa 2, inside this kappa 3, this is basically kappa 1. So these are the driving forces for chi subscript I1. So this is 1 1, 2 1 and 3 1. On the other hand, rest of the chi's are primarily driven by the warping. These are driven by the out of plane warping, and all of these would be driven by the in plane warping, and that's why you see no effect over there. In other words, almost similar to an identity matrix is what you're generating over here. So now we have further generalization, because we're talking about strains as generalized strains, 1D generalized strains. So it includes not only the gamma 1 1 and the gamma 1 alpha, which we already introduced, it also includes the moment strains, which again you are aware of, which are the kappa 1, kappa 2 and kappa 3 associated with twist and the bending curvatures. Now we introduce an additional 1D generalized strain. Once again, the yellow is the difference between the red and the green. So that's basically your big Ki minus small ki. But remember that the big Ki are measure numbers along the big B basis. The small ki's are measure numbers along the small b basis. And it's the difference between those measure numbers which is what is your kappa I. Okay? And this again will be consistent with the vector dyadic definition that we will give, similar to the vector dyadic definition that we gave for the gamma.
Do we have the keys for this?
Yes, we do. So we would have similar vector dyadic definition for the curvatures as we did for the one-dimensional generalized strains associated with the forces, that is the force strains, and that is consistent with the fact that this will be along the big B and this will be along the small b, and then you have the difference as the kappa i's. So kappa 1 here, of course, is the elastic twist per unit length. and kappa alpha, that is both kappa 2 and kappa 3, are elastic bending curvatures about the appropriate directions. Next, you have kappa I expressible in a variety of ways. Just like rotation can have various kinds of parameterization, kappa I can also be expressed in variety of ways, just as the direction cosine matrix. We will look at certain representations. There are a few others which are listed in your textbook. You can take a look at them as well. Once again, we go into the interpretation of kappa I in a physical sense before introducing its vector dyadic compact relationship with the initial twist curvature and the final configuration, what is the big K. Okay, so the kappa I is interpreted once again as a measure number of a difference of two vectors. The vector which is being subtracted is basically nothing but your initial twist and curvature. The vector which is basically from which the small k is subtracted is the big K, but not by itself. Before the subtraction is done, you basically have to pull back this k to the small b basis and then only subtract the small k, and what you get because of that operation is basically your kappa.
So that means we should put some function of capital K minus small k, right sir? The first line we can interpretation.
In this?
Yeah.
No, this
because
is
when you are Ki interpreted as measure numbers, that is we have to pull back Ki in the small b system, right sir?
yeah, that's correct. See, your small k and the kappa I are in the small b system.
Yeah.
It's only the big k's which are in the big B system. Okay.
So
Because that is more convenient for us also to visualize what is happening for the cross section, because we are more familiar with the undeformed geometry. So we can interpret kappa 2 as the curvature in a particular direction, but once the rotation has happened and you want to interpret, let's say if instead of this I wanted to have the kappas along the big B system, then it would become a little more complicated to interpret what actually it is.
then that subtraction means like complicated as well, because we don't know what we have, because bases are not same, right sir? Because
No, bases are not same, but once the bases are defined, it is much easier to get the measure numbers of anything associated with the deformed configuration along the big B system and anything associated with the undeformed configuration along the small b system. So all that you are doing is you are taking those measure numbers and subtracting them to get your kappa I. And that becomes consistent with the way we are defining here your kappa as a vector. Now, as a vector, it doesn't matter along which basis it is expanded. So this is a vector equation where kappa is a vector. So if you want to expand it along the small bi system, then it becomes the same kappa I multiplied by the small bi. But if you expand it along the big bi, it would not be these kappa I, it would be some other kappa I which should have a different meaning.
so that means when you will operate that Ki should be first pulled back to the
Right.
right sir.
Right. So you're pulling back big K because it is defined in the deformed configuration. That has nothing, again, this pullback has nothing to do with the way I have these components. The components, this is a component level equation, it's basically measure numbers, is a scalar equation. Okay. Whereas this is a generic equation, which is a vector, irrespective of about which basis small k is defined, which basis big K is defined, which basis kappa is defined, this equation always holds good. But for this equation to hold good, a specific way of expanding each one of them is necessary. That is, this along the small b system, this along the big B system, and this along the small b system. So it's only then that this equation will hold good. But this equation holds good always, irrespective of how you expand them. Okay. So your kappa is nothing but, if there were no, this CBB were not there, it's just K minus K, but just that there is rotation, and that's the reason why big K is different from small k. If CBB were identity matrix, then your big K would be equal to small k, and it would become just K minus K equal to 0. Okay, it's because there is a difference between the small b and big B system that you have a big K which is different from the small k, but you cannot make that subtraction directly. You have to pull it back from the big B system to the small b system. In other words, from the deformed configuration to the undeformed configuration, reverse of what happens in reality. So once you do that, then you can do the subtraction, and then you basically end up with the so-called moment strain vector. So next, let's look at what we get out of that deformation gradient tensor that we already developed. One of the things is, of course, its symmetric part minus the identity matrix. So we will take chi plus chi transpose. Remember that we got expressions for all chi ij for I and j running from 1 to 3. So now we can get chi plus chi transpose divided by 2 minus delta, which is the identity matrix, the 3 by 3 identity matrix. When we make that, you basically end up with what you defined as E in the previous class, and that of course has direct relevance to the 3D strains. So it's an important aspect apart from the local rotations, which is also something we'll look at later. So first of all, let's recollect that the definition for E was chi plus chi transpose divided by 2 minus delta, and we also defined this quantity root g as nothing but 1 minus x2 k3 plus x3 k2, where k2 and k3 are the initial curvatures associated with the reference curve in the undeformed configuration. And then of course what we had in the previous slide, which is kappa is equal to ki minus big ki minus small ki. Now let's start with the simplest things first. We got expressions for chi 2,3 and chi 3,2, or simplified that and found that to be equal to 0 because of the fact that we ignored W2 and W3, and therefore if you substitute into this, it's quite obvious that E23 and E32, which are the off-diagonal components, two of the off-diagonal components of this. Of course, E is a symmetric matrix, so it's quite obvious E23 and E32 will always be equal to each other. But in this case, happen to be 0 as well. It's consistent with the ad hoc assumption that we made of 0 in plane warping components W2 and W3. Similarly, again, because of the fact that W2 and W3 are equal to 0, we had chi 22 and chi 33 equal to 1, and therefore E22 and E33, as you can see from here, will be equal to 0 because it will become 1 minus 1, and therefore you have them as 0. So in other words, remember that we also derived the expressions for gamma in two different cases. One is the small local rotation case, which was valid for class R beams. There we saw that gamma is, the leading term is just E itself. So in other words, what we are seeing are expressions for the 3D strain as well in an R class beam. So in an R class beam, if we were to ignore the in-plane warpings, then we would come to the conclusion that these two normal strains associated with the cross section are basically equal to 0, and basically the corresponding shear strain E23 or E32 is also equal to 0. In other words, your gamma 23, uppercase gamma subscript 23 would also be equal to 0. So next we come to the little more complex situation, which is chi 1 1. Again, it is chi plus chi transpose, both are equal to each other because it's a symmetric matrix, and then you have to divide by 2. So it's nothing but chi 1 1 itself, but just have to remove my 1 from that. So you have this expression for chi 1 1. From this I have to subtract 1, but I cannot just remove this 1 because there is a denominator divided by root g. So when I subtract, it will become minus root g into these square brackets, and root g itself has this expression. So this 1 will get subtracted with this 1, so there will be no more 1 there. But in addition, you will also get a plus x2 kappa 3 and a minus x3 k2. So that, plus x2 k3 and minus x3 k2. So that's basically going to convert your big k2 into kappa 2 and a big k3 into a kappa 3 because of this particular relationship that big k minus small k is nothing but kappa. So that basically is invoked over here, and your big K2 becomes small kappa 2 and big K3 becomes kappa 3, and that's the expression. The rest of it pretty much remains the same. Next we have chi 1 2, which is basically the shear strain which will lead to the shear strain associated with the 1 2 direction. For that we need not only chi 1 2 but also chi 2 1. So that we add those two, divide by 2, and there is no subtraction because it's a 0. So then basically this is what happens. So you end up with this expression, and here, whereas in E11 the leading terms were basically the extensional strain of the reference curve and the bending curvatures, the rest were all warping related terms. In E21, the main leading term is basically the torsion. The torsion causes shear strain. In addition, if the beam were a short stubby beam, or it was made of a composite where the matrix has a low shear modulus, for example, in such situations the transverse shear strains can be large, or something which has to be considered, but still it would be something which is not as large as this, as we shall prove later on. But basically that is the next important term over there for our so-called class R beams, where you have the transverse shearing strain contributing to the corresponding strain associated with the 1-2 direction. And then again you have terms associated with the one-dimensional warping, or rather the out-of-plane warping. Now the out-of-plane warping, again it's important to see that sometimes it can contribute to the local rotations. So remember that any warping measure along a particular direction taken when its derivative is taken with respect to any other direction, let's, for example, in this case we have only W1, forget W1 comma 1, which is W1 prime, the other two, which is W1 comma 2 and W1 comma 3, contribute to local rotations. Okay, so that in this case is coming through your lambda 2 and lambda 3, because you wrote W1 as lambda times xi, and lambda was the only thing which was functions of x2 and x3, and therefore your W1 derivative with respect to 2, which is nothing but in this beam, if the 2 direction was along the width, so W1 is along the x1, and therefore W1 is along the length. So basically what we are saying is, how does W1, which is basically coming out of the plane, how is it varying with respect to the x2 direction? So in other words, basically this kind of rotation is what we are talking about, not for the cross section as a whole. This is warping and therefore local rotation. So there are small elements which basically rotate in this particular direction. So that is a local rotation which could be different at different points. So that is your W1 comma 2. Similarly, you will have a W1 comma 3 which could be different at different locations, and these are basically contained in the so-called lambda subscript 2 and lambda subscript 3 terms over there. So there might be situations, for example, when you have, because all of these, whatever we are deriving, is not for a specific class of beam. It is for whether it is class R, class S or class T, these E values are valid. But what is gamma will be different. So in other words, you would have additional terms coming for the 3D strain in addition to E, because of the contributions of those local rotations. So that's what we will see when we go to chi tilde next. So again you have E13 having an expression very similar to what you had for E12, just the 2's and 3's are getting replaced, that's all. So once again, just like here, the main contribution was from torsion. Here also you see the main contribution is from torsion, just that the coefficient instead of x3 happens to be x2. So once again it's the kappa 1 which is the driving force, is the driver. Okay, and again instead of the transverse shearing strain gamma 1, 2, you have the transverse shearing strain gamma 1, 3. The rest are all the contributions of the out of plane warping. This is out of plane warping as it is, and this is out of plane warping in the form of a local rotations, basically lambda 3 which is involved, which is basically coming from a W1 comma 3 kind of a term. So now let's look at local rotation specifically, because we related the deformation gradient tensors skew symmetric or anti-symmetric part basically to the local rotation. So that's what we will explore here, because we have got the expressions for chi. We can subtract chi transpose from chi, divide it by 2, then we would get chi tilde, and we know that the leading portion of phi tilde is nothing but chi tilde itself. So then from that we will be able to, of course it's a skew symmetric matrix, so only 3 independent components which are all in the off diagonal, which are all off diagonal terms, are of interest to us. And so those 3 components will be the 3 local rotations in a 3-dimensional sense if we want to look at it. And in that sense we would explore what is the driving force for each one of those local rotations. So let's first of all look at phi1 directly employing this particular formula, but in a component form or a measure number form is nothing but phi1 is nothing but chi 32 minus chi 23 divided by 2, because this phi tilde will involve phi1, phi2, phi3 populating the off diagonal terms with appropriate signs. as we have discussed before. So once again, this is the simplest situation. So both chi32 and chi23 happen to be 0, and therefore your phi1 is equal to 0. So in other words, there is no local rotation associated with the one direction. So this is basically phi1, that is, no element in this particular cross section rotates about the x1 direction. Why? Because you don't have W2 and W3. If there is no W2 and W3, there is no way each small element in this cross section can rotate differently from other elements in the same cross section. Whatever rotation happens will be as a rigid body. So because there is no W2 and W3 warpings which are basically involved. So that's why you see phi1 equal to 0. Whereas phi2 and phi3 would have non-zero contributions. And as I said, it's consistent with the ad hoc assumption that we made of 0 in plane warping. Next we go to phi2, which is now equal to chi subscript 1 3 minus 3 1 divided by 2. When we put those expressions for chi 1 3 and chi 3 1 and simplify this, because we know the expression for root g as well, so we'll take that. So once we do that, we get this as the phi2. Similarly, we get this as the phi3. So these are non-zero local rotations caused by W1 varying with respect to the x2 and the x3 directions. Because it varies with respect to the x2 and x3 directions, phi2 and phi3 are non-zero. So and these are the expressions, and they are directly related to your lambda xi, but in turn they are also including the transverse shear strains. Okay, so you see that this is basically coming over here. You have this 2 gamma 1 2 over here and 2 gamma 1 3 over here. Okay, in other words, they are not explicitly coming through the warping, but they are coming through the so-called rigid body like rotation into the so-called local rotation. But because of the fact that they are functions only of x1, they are not true local rotations. In other words, it is the same. It is on a given cross section, x1 is fixed, it's only x2 and x3 which vary, and therefore the contributions from your gamma 1 2 and gamma 1 3 to phi2 and phi3 remain the same throughout. So that is the difference between this particular term and the rest of the terms which are contributed directly from the warping. So later on we will prove that irrespective of what class of beams you take, some of the terms in phi I, this is of course for a specific ad hoc example, but it should be valid for this example as well, because this is a special case of the general example. So in a real situation there can be some special situation where it so happens that W2 and W3 are 0. But keeping that aside, even in the general case, we will see that some of the phi terms, even when you get the general expression, will always be of the order of the strain. Remember that the maximum of gamma ij anywhere in the domain of the beam at all times of interest, basically we said is epsilon hat for all components. So basically it means that the phi terms, some of them will always be of order epsilon hat. Remember that in general you will have not only phi2 and phi3 but phi1 also, and each one of them will have a large number of terms, and some of those terms in each one of these expressions you can find out and show that they would always be of order epsilon hat, because if they were not order epsilon hat, then the strain gamma to which they contribute will turn out to be larger than epsilon hat, which violates our initial assumption that the epsilon hat is defined as the largest value of the strain component anywhere in the beam. And whereas the other terms, the remaining terms, some terms are always 0 irrespective of the class of the beam, but then the remaining terms would also be of the order of epsilon hat if you take, for example, class R beams, because that is the simplest case where warping and local rotation do not make much of an impact towards the strain energy. Whereas when you go for the T class or the S class beams, you would see that the warping and local rotations make much more larger or important contribution to the strain energy, and in such situations you will find that some of those terms would not be order of epsilon hat but larger than epsilon hat. Okay, but for classes T and S beams, as I said, phi can exceed the order epsilon hat. In other words, it would be a lower order term. And what we will do in the next slide is to illustrate two such possibilities. We will take an example of a T class beam and an S class beam. Without going into the entire derivation, we'll just point out why it is so that some of the terms of Pi can become larger than epsilon hat. We will use some of these expressions that we already derived, which were derived without assuming what is the class of the beam. Just the only thing that was assumed was W2 and W3 are equal to 0. W1 was let free, and of course with the assumption that it is broken, it can be broken in or decomposed in this particular way into lambda and xi. But even with these expressions, we can show what will happen with the T and S class beams and how some of these terms can, for example, exceed the order of magnitude epsilon hat. In other words, it's a lower order term. One term of interest would be, for example, this. You know that if it was a S class beam or a T class beam, the torsional stiffness will be very low. So in other words, the initial or rather the twist per unit length due to the torque can be fairly large. So in other words, your kappa 1 can be quite large. And you have in let's say in a strip, if the x2 direction is this and x3 direction is this, then you know that the x2 order of magnitude is the width, which is pretty large. So in other words, your kappa 1, the reason why it is large is because of this thickness. So typically it will be of the order of magnitude of epsilon hat divided by h, which is the thickness, whereas it is getting multiplied by x2, which is of the order of b. So it becomes b into epsilon hat divided by h. Okay, and so if you retain epsilon hat as it is and take the h here, it becomes b by h into epsilon hat, and b by h is a large quantity because the width is large compared to the thickness. So it's possible that this term contributes to phi2, a local rotation, something which is larger than the strain itself, and that it is in such situations that local rotations become important. In other words, the contribution of warping to the strain energy becomes critical. So let's look at that a little more detail. Local rotation in classes T, S and R beams as well. So first of all, let's look at this example of a class T beam, which is an I section. So you see these two flanges over here, and you have a web. Let's say we introduce three separate coordinate systems associated with the undeformed configuration itself, associated with the web. Let's say is the y and z coordinate over here, and similarly with the right flange you have y r and z r. Let us say x, of course, is the coordinate or the coordinate Cartesian coordinate along the length of the beam, and then you have along the left flange you have the coordinates, let's say yl and zl. So basically the y's are along the widths of each of those component strips, and the z's or z's are basically along the thickness of each of those three component strips, because each one of them can be considered as a strip. So now we'll also look at a class S beam, which is simpler to visualize. Once again, it could be a part of the class T beam. You can take any one of these component strips and then visualize it separately, or it could be a separate beam which is in a thin rectangular cross section shape. So here again, x1 is along the length, x2 is along the width, and x3 is along the thickness. So for the strip, for example, if we take up the same situation that we derived in the previous slide, that is where we ignore, let us say, W2 and W3, which is not right in fact, okay, because W2 and W3 can be large for this situation. But just from whatever solution we got from W1 itself, we can make quite a few inferences which will be useful, and that's what we are trying to do right now. Okay, so it's a subset of the truth. Okay, so now let's look at this. We have xi is equal to kappa 1 in such a situation. Of course, we are not proving it here, but that's what it will turn out to be if you do, for example, a 1D analysis with this. Then you will see that the amplitude of the W1 function, the warping, out of plane warping, turns out to be kappa 1. In other words, it is the twist which basically drives the out of plane warpings. If there were no twist, there would not be any out of plane warping in such a situation. Again, of course, that is the main thing, but in reality there could be other situations as well. But basically, this is something you're familiar with when you study torsion of non-circular cross sections as well, that when a circular cross section is twisted, the cross section remains plane, but when a non-circular cross section is twisted, you can get out of plane warping, and that out of plane warping will be dictated by how large your twist per unit length is. So the larger the twist per unit length, elastic twist per unit length, the more the warping that is going to be. So that is basically what this indicates. On the other hand, because it is a rectangular cross section, it is proved that the Saint-Venant's warping function for that is nothing but x2 times x3 with a negative sign. According to the sign convention that we are following. So that basically means that the W1 will now be given by minus kappa 1 x2 x3. Okay. Now again, the x2 range is from minus b by 2 to plus b by 2, where b is the breadth, and x3 will be from minus h by 2 to plus h by 2, where h is the height of this particular beam or the thickness, right? So and that
actually that warping function is under the assumption you can only give the end moment.
That's correct. Yeah.
So like we cannot consider this if our loading conditions are different.
Exactly. That's correct. That's correct. It's just only for illustration purpose. Okay. So when we go to the general case, we will not even bring this into picture. But what you're saying is right. It's only under those conditions that the function, as we wrote, the Saint-Venant warping function is valid. Here. So in this case, h is very small compared to b. The height is small compared to the breadth. So in the previous slide, we had an expression for one of the local rotation components, phi2. We saw phi1 was 0 under the ad hoc assumptions we made. Phi3 was non-zero. But let's just focus on phi2 for the moment. So phi2 is given by this particular expression. Apart from the transverse shear and the warping, it's basically this term that we were saying that it could be a troublesome term when you're basically dealing with either a strip or a T or I section or anything which is of class T. Okay, so basically now we are focusing on the rectangular cross section, because this is valid only for the rectangular cross section, not for the I beam. So for this kind of a situation, now let's see what could happen. Your phi2, now we can substitute those values of lambda and also the lambda 2 and lambda 3, because lambda 3 would be derivative of this with respect to x3, which is just minus x2, and similarly your lambda would be just minus x2 x3. So we're basically substituting that, and we are also substituting the expression for root g as 1 minus x2 k3 plus x3 k2. So this is the expression that you get for this. Now if you look at it, even after substituting that, there is no cancellation of any terms which takes place, and still you end up with one of the main terms of your phi2 is basically your x2 kappa 1, which you basically see over here. Okay, so the magnitude is what we are interested in over there, and that magnitude will be much larger than minus x3 kappa 1. Okay, if you let me just go back and look at this expression for the strain E12, for example, over here. Remember that the torsion is the main driving force there as well. So it's basically this term which contributes to the torsion over there. Now we know that E is the main contribution to the 3D strain, just like all the other E's are. Okay, so just like any of the other EIJs, your E12 or E21 should also not exceed epsilon hat, because that is the maximum strain the material can handle, right? So if that is of the order of epsilon hat, then none of these terms can be bigger than epsilon hat. So similarly, this contribution from the torsion should also be not bigger than epsilon hat. Or in other words, from that we can guess what could be the maximum allowed value for kappa 1 before the material fails. Before the material fails, the order of magnitude of the strain would be epsilon hat. So order of magnitude of kappa 1 would be epsilon hat divided by h, because x3 is the coordinate along the thickness direction, which varies from minus h by 2 to plus h by 2. So order of magnitude of this is h, and therefore the order of magnitude of kappa 1 is epsilon hat divided by h. This is clear, right? Now we go back to that expression for phi2 that we had over there. Okay. So now if you see the expression for phi2 that we have, the leading term there in the E12 was x3 times kappa 1. Here the leading term is x2 times kappa 1, whereas the order of magnitude of your x2 is b. Okay. Now we know that this is much larger than your x3 kappa 1, which is what the strain is. So in other words, because from this fact, from the expression for E12, we determine that kappa 1 is of the order of epsilon hat divided by h. Now if we compare that, put that here, kappa 1 as order of magnitude epsilon hat divided by h, we see that this becomes b by h times epsilon hat, and this is what I had already pointed out too as a preview. So basically your phi2, the local rotation about the two direction, can be larger than epsilon hat. It can be larger than the strain. Remember, rotation is also can be considered as a non-dimensional kind of a quantity. So basically comparing it with the strain, and whose largest value is epsilon hat, and we are saying that your phi2 can be bigger than that. So if h for on the other hand, when you go from a strip, let us say, to more like a rectangular cross section, you start increasing the thickness of the strip so that it becomes more like a class R beam, which is a rectangular cross section class R beam. So as you keep increasing h such a way that order of magnitude of the breadth and the height are not different. They can be numerically different. B and h can have different numerical values, but they don't differ by an order of magnitude. They are of the same order of magnitude. In such a situation, of course, your x2 and x3 would be of the same order of magnitude. Once again, the same expressions would be valid, and therefore your kappa 1 would now be still order of epsilon hat divided by h, but here it would become epsilon hat by h into b, but b by h is of the order of 1. Okay, and therefore your phi2 will also be of the order of epsilon hat. So that is the difference you see between a thin strip and a thick beam, rectangular cross-section beam. The only difference is that your local rotations start coming down in magnitude. In other words, they become higher order contributions to the strain energy, and therefore not as important as they were for the strip. So that is if class S beam is slowly morphed into a class R beam, your local rotations start becoming less and less important and eventually negligible. So now let's look at the strain. Remember, in the previous class we had two separate categories. One is the small local rotation category, where that parameter R that we introduced as a power basically was greater than 1, and in other situation where R is less than 1 and above half. So let's look at both those situations now. Gamma ij is obtained by substituting the expressions that we already obtained for the preliminary example in terms of E and phi tilde into the expressions for gamma. So there were two categories. One is the small local rotation theory, SLR, let's call it for abbreviation. So in that situation, the main term was E. The other terms were of the order of the local rotation squared, or the local rotation, maximum local rotation times the maximum strain. So which were higher order terms. So just taking E itself as gamma was good enough. So that was for the class R beams. So strain measure numbers are just the elements of E for the small local rotation theory. The other case was the MLR, or moderate local rotation theory. In other words, we're not calling it large local rotations, because the large rotations are associated with the rigid body like rotations of the cross section. Anything which happens with the local rotations is indeed small, just that within these small values we are making a distinction between what we within quotes is small and what is moderate, right? So in this situation, we not only have the term E, but also terms which depend on phi tilde, which in turn depends on small phi1, phi2, phi3, the local rotations, and therefore you have a phi tilde squared by 2 term and a combination of phi tilde and E term. So totally 3 terms are there. This is 1, 2 and 3. So these 3 additional terms, all depending upon the local rotation, have to be added to the small local rotation theory's expression for the 3D strain in order to obtain the expressions for class T and class S beams, especially class S beams with axial loading. So terms of order epsilon hat in phi tilde, basically like for example 2 gamma 1 alpha, but actually you will see that later on when we do for class R beam derivation, it is not even order epsilon hat, but in fact smaller than that. It is epsilon hat times A by L. But let's keep that aside for now. So terms of order epsilon hat in the phi tilde expression are discardable when phi tilde is either squared or multiplied by E. Because remember that the only ways it contributes is as its square or as a product with E. And we already know E has the order of magnitude epsilon hat and phi tilde has the order of magnitude of this phi. So basically any terms of order epsilon hat in the expression for the local rotation can be discarded, because anyway they are not going to contribute if they are going to be squared or multiplied by E if they are of the order of magnitude epsilon hat or higher order terms, right? So ad hoc arguments are therefore unnecessary to remove these terms. In other words, automatically it happens because of the fact that they are small and in turn they are related to the orders of magnitude of the cross-sectional dimensions and the length, etc. that we take into account. So therefore additional assumptions over and above what we have already made are not necessary in order to drop out those terms, smaller terms in phi tilde. So it can be proved later, it's proved in your book as well. If cross-sectional dimensions are, let's say, of the order of magnitude A, for example in a rectangular cross-section of breadth B and height H, B and H are both of the order of magnitude A. So in such a situation, if cross-sectional dimension is of the order of A, then the warping is almost always order of epsilon hat by A. The reason is that some of the 3D strains, like let's say your gamma 3,3, gamma 2,3, gamma 1,3, etc., would depend upon the derivatives of warping with respect to the 2 and 3 directions. So not 1,3, it's gamma 3,3, gamma 2,3 and gamma 2,2. So those would depend upon the derivatives of W2 and W3 with respect to X2 and X3. And because X2 and X3 are both of the order of magnitude A, therefore the warping can only be of the order of epsilon hat times A. It cannot be bigger than this. If it were bigger than this, the contributions to the strain components gamma 2,2, gamma 3,3 and gamma 2,3 can become bigger than epsilon hat, which violates our initial definition of epsilon hat as the largest strain which the material can take. So also recognize that the cross-sectional dimension, for example, has to be smaller than the length of the beam in a statics problem, and in a dynamics problem it has to be smaller than the wavelength of deformation associated along the length. In addition, the initial curvatures can also not be very large. If K is a vector consisting of the initial twist and the initial curvatures in the two directions, then basically K dot K square root basically gives a measure of the equivalent radii of curvature due to the initial curvatures. So basically this becomes nothing but the radius of curvature, the mean radius of curvature due to the curvatures in all the three directions. And you can see that A has to be small with respect to that as well. Otherwise, even in this case where, for example, let's say this beam is turning around itself, so this is a beam which has an initial curvature like this, even in that case you see that the order of magnitude of the curvature basically is, the radius of curvature is the same as the cross-sectional dimension. It cannot be smaller than that. But in most situations, most engineering situations, you don't have such extreme curvatures, so you can for a very large class of engineering beam problems, A will be small compared to the initial radius of curvature, and that can take care of a large number of initially curved beam problems. So in such situations, we have to ensure that your K is such that A is small compared to 1 divided by K dot K, and that would simplify the theory to a large extent. Otherwise, of course, you would have to add the terms associated with initial curvature to the strain energy, because their contributions can become fairly large. These geometric small parameters would be useful later when we rope in the variational asymptotic method, apart from the small term associated with the physics of the problem, which is basically because of the material. So these are geometrically small parameters, by which I mean A divided by L and A divided by, if I call this as R, then A divided by R. So these are the small parameters which help the variational asymptotic method to be applied to a beam. So the purpose above is to merely to show the simplest way of obtaining the strain. So there was no other need for us to make that kind of an assumption that we made at the beginning. It's only to show how simply it can be derived. Even in the general case, as we shall see, it is not that much more complicated, just that we wanted to visualize what is happening more clearly, and that's why we brought in this example. So in the next class, before we take up the general case, we'll revisit again some of the terms which are involved with the expansion of the strains based on both the small local rotation and the moderate local rotation theory, and then we'll see where are those strains coming from physically and what is their role which is played in terms of physical intuitive understanding of the beam deformations. Thank you.